AI techniques that we use for the signal analysis. So me and my colleague, worked on this project, and we managed to implement explainable AI in our project. And the project yielded a very good responsiveness and was useful in developing this idea. So we shall dive right in. So the purpose of this presentation is to explain the AI techniques used to analyze, interpret the ECG-based speech signals. So the key topics are going to look at, we have layer-wise relevance propagation, which is LRP, speech spectrogram analysis with SHARP. Then we also have waveform decomposition. We have temporal output analysis and the Fourier transform analysis. So we were mainly working with audio data. That's why we employed these 5 explainable AI techniques to aid us work on these audio techniques that we can have very good speech signals. So the goal was to demonstrate how these methods contribute to AI-driven speech translation. So layer-wise relevance propagation. So in layer-wise relevance propagation, we were actually looking at how to visualize the different input features to contribute to the signals. So we were looking at the specific audio features that we were able to visualize and understand the relevance of the parts of the audio clips that are very vital in the model predictions. And also we were able to backtrack each model layer by layer. So in the process, the model was able to make a prediction. And the relevance is backtracked layer by layer. Then we generated heat maps to show influential features. So what is the use case of the layer-wise relevance propagation? So it was to identify the ECG signal components to the speech translation. So it helped us to understand the components that are very impactful in the speech translation. We were able to look at the components in the audio speeches that were very relevant in the process. Then we have the spectrogram analysis we show. So why spectrograms? The spectrograms were converting audio into time frequency representation. So they were able to convert audio into time frequency representation. So we were able to view different aspects of the audio clips and able to understand which components are crucial in the project and which components are crucial in the implementation of this signal translation device. So the application would identify which frequencies and time segments in a corresponding audio clip that would influence predictions. It would provide insights into how AI interprets sound patterns. So these were the crucial parts of the spectrogram analysis. We managed to draw spectrograms for the best 2 models and the worst 2 models. So we're able to analyze the patterns in each of those models. We're able to tell which components were crucial in determining the multi-strategy sparse learning translation of the signals. So next is the wave decomposition. So the purpose of the wave decomposition was to break audio signals into components such as pitch, intensity, and noise. So we break these audio clips into different patches. So the use of these patches was for us to understand which part was very crucial in the process, which part provided better results. So we use the techniques such as short-time Fourier transform and the empirical mode decomposition, EMD. So the benefit was to help us isolate features crucial for accurate voice reconstruction. So after breaking the audio signals into different components such as pitch, intensity, and noise, we were able to tell which component was crucial in our project, able to tell which component was very important in developing a very steady voice, a very steady pattern for translation. So the next technique we employed was the temporal output analysis. So the objective was to track how model predictions evolve over time. And then the approach we used, we compared AI predictions frame by frame. Then we also detected temporal dependencies in speech patterns. So what was the value? What was the use of this analysis? So we were able to understand how AI maintains speech consistency. So the temporal output analysis helped us maintain our speech consistency. So the model we developed was able to be consistent in doing the same thing at the same, in providing accurate results, consistent results. The results are always the same, and we're able to spot a pattern for each video. Do best to us. So lastly was the Fourier transform analysis. So what is a Fourier transform? A Fourier transform converts signals into frequency components. So we were using this technique to convert the signals into frequency components, because these signals would have time domains, and these time domains could not easily be mapped to our model. So you had to convert these time domains into frequency domains so that they can easily be understood. So the relevance, we identified dominant frequency ranges in prediction, and we filtered out unnecessary noise. So the application, it determined which spectral features are most useful for speech synthesis. So we were able to identify which features are useful in the process. So lastly, so the layer-wise relevance propagation explains feature importance. Program reviews time frequency influences, waveform decomposition, isolates critical components. Temporal analysis shows speech consistency, and Fourier transform identifies key frequency. The next steps we looking forward to optimize feature selection, enhance model interpretability, deploy. Then we shall deploy and test the model to see its accuracy and proceed. That's been Simo Emmanuel. Thank you very much.